science like there's no tomorrow.
Hello everyone, welcome to the third block of lecture number 12 of the Financial Engineering course. Today we will finish the lecture with the final block. In the previous lecture we have finished the block with an expression for CVA, and that expression involved probability of default of counterparty, and also we had exposure calculation. In this case, in this block, we will start with certain approximations which are considered to be market standard for estimating CVA. And this also has to do with the so-called wrong way risk. In the second part, or in the second point of this lecture, so in the subsection of this lecture, we will discuss BCVA. BCVA addresses the problem of so-called symmetry. So if we, for example, charge a client based on his default probabilities, certain amount of money to price when we price a derivative, a client may see us also as a potential defaulter. So we may also default on our obligations. Therefore, client will see us also as he will also charge us additional amount to compensate for that risk. If the amounts that we would like to charge our client and the client would like to charge, they are different, this means that the transaction will not take place because the prices expectations from both sides, they don't match. And this is addressed by CVA or BCVA. In BCVA, we actually, in the evaluation of derivative, we are not only taking into account the possibility that the client may default, but also that we as institution may default. And this is related to the so-called depth value adjustment or DVA. In next point, we will discuss the FVA, so again, application of calculation of expected exposures or expected positive exposures and expected negative exposures. So I will show you a very small extension of CVA and BCVA on how to arrive at the FVA, and also we will discuss the approximations often used in the industry. Here, the final point before the summary is so-called trade attributions. So imagine a scenario that a risk manager would like to see which of the trades in the portfolio contributes to the most of the CVA seen on the portfolio basis. This so-called trade attributions for CVA addresses this issue. In general, if you would like to calculate all individual CVAs for all the trades, then we have a problem that sum of CVAs is not equal, it's not additive, it's not equal to the CVA of a portfolio. In this point, we will discuss possibilities how to make this kind of avoid this problem of additivity, such that let's say certain representation, or how to weight CVAs in a portfolio such that they add up nicely to the overall CVA of the portfolio. Finally, we will have a summary of this lecture and homework. I have prepared two exercises for today. The one exercise will involve simulation of the portfolio, for a certain portfolio, and calculations of CVA and also potential future exposures. And second exercise will be related to the closed form solution, where you have to simulate some derivative and compare it against the closed form solution discussed in the previous lecture. Enjoy the course! From the definition of CVA, we see that in order to calculate this adjustment that we have to incorporate in the risk-free pricing, we need actually a joint distribution between default probability and the exposure VT. So that's basically a problematic issue. Of course, this exposure VT, already before I've mentioned that this VT is essentially our portfolio, which is driven by stochastic quantities. So as such, you can consider VT, capital T, to be a stochastic variable. Of course, you won't be able to derive the dynamics for this variable, because typically it will be very much complicated, given also that your portfolio may change in time. That will be very difficult to find these dynamics. However, you still need to have a correlation between a time of default and also risk factors. It's typically rather problematic issue. Let's see now how we can approximate that and what are the market approaches on how to handle this correlation between or joint distribution between default probabilities and also risk factors present in the market. So first we start with the CVA definition from previous slide. So this is the adjustment we have to incorporate in a risk pricing. We have the recovery rate or the loss given default. This is of course constant, so it doesn't really matter in this derivations. We have this expectation under Q measure. We discount with from the default time until today, so until time t. And then we have an indicator. So this quantity will be only taking place if default happens before the final payments of our underlying swap or other contract. And then we have this maximum of this exposure of this contract at time tau. And then we have capital time t. This is the end of the contract. What we can do, we can perform first conditioning on, so tau property conditioning on the time of default. Then what we do is basically the following. So of course, this sigma field here inside, because we are conditioning here on t, tau obviously is a larger sigma field because this will happen after today. So this is what we can do using the tau property of expectations. And of course, then this indicator function, it is measurable. We can take it outside of the expectation. But still, we need to have a joint distribution between this sigma field here, this expression, and also this indicator function. So this is, although it looks like an expectation, this part is still a stochastic quantity. And this stochastic quantity, it's correlated with time of default. So this is something that to keep in mind. So to get this, you need to have a joint distribution of the two. Now, this is also important. Often in terms in financial engineering or in general in finance, you would often hear terms like wrong way risk and right way risk. And this has to do with the correlation between exposures and default probabilities of counterparties. So if we have a positive correlation between default probability and exposure, so this means if your counterparty, your exposure to the counterparty increases, so you can say you are essentially getting more in the money, your P&L is increasing. However, at the same time, counterparty has a higher probability of default, that's considered to be a wrong way risk because your exposure increases together with probability of default of the counterparty. And that's essentially from one side, you can say you are happy because your P&L, future discounted future cash flows increase. At the same time, because the counterparty has more risk associated with meeting the obligations to pay you back these amounts, then default probability may increase. And that's called wrong way risk. And of course, the opposite is called right way risk. There are a few ways, of course, we will try to approximate. Of course, in practice, it's difficult to estimate this correlation between different risk factors and default probabilities. You have to go into the historical data. Otherwise, it's very difficult to get from the, let's say, exotic derivative, or they're not really market instruments that you can really imply those correlations between default probabilities and risk factors. Also, what would be the joint distribution? It's another question, how to model the time to default. However, there are some possibilities. We can impose correlation structure, maybe not necessary from terms of pricing, because if a client comes, you may want to, of course, see this correlation impact. But from a risk management perspective, it is rather crucial to see what is the risk profile, how this exposure of a counterparty would be impacted if the probability of default increases. And those elements are, from the risk management, very much important. And the ways to impose the correlation, so if we assume independence between the two, would be, for example, via stochastic process, via hazard rate process for the time to default, to be one possibility. And the second would be via populace, so kind of imposing a correlation structure on independent random variables. Those two techniques I'm not going to discuss in this course, but there are some classical articles you can look up online that will provide you how, in simple way, introduce this correlation. Let's take a look now at our approximation for CVA, because at the end we would like to implement this CVA correction. We see again everything is the same as we had before. Now the outer expectation becomes integral, and then we have inner expectation. So we have exactly the same. So discounting of the positive exposures to time tau. On this is conditioned that tau is equal to s, and we multiply with probability of default of density of tau. Of course, this part is equivalent with this expression, so we can also look at the CDF, the time to default or default probabilities. of the counterparty, and then we can have this. We have this expression. So if integral over this conditional expectation multiply with the time increment or the CDF or density in that time interval. So actually, this is the difference in CDFs in the infinitesimal small time step. And what is the market approach? Of course, is to assume the independence between tau and v, and then essentially to approximate this conditional expectation by expected exposures. So you can see this expected exposures in Ti is defined here. So this integral becomes a summation. This is one approximation. And of course, the second part is that we are not taking into account the correlation between the time to default, the default probabilities, default random variable, and exposures. So that's the big assumption here. But of course, from the implementation perspective, this is very straightforward because we have to just integrate in time expected exposures. So this is something we already have done in this lecture. We have to multiply with QTI minus 1 Ti, and this is QTI minus 1 Ti is defined here. So it's a difference between CDFs of a random variable tau minus this is time Ti minus CDF tau Ti minus 1, and this will represent the default probability in this particular interval. So we calculate exposures in one interval and we multiply with probability of the default in that interval. That is of course equivalent to this indicator function that default will happen in between these two time points. So overall, how we can express our CVA? It are three main elements. The first one is this 1 minus recovery rate called loss given default. Second, we have to multiply probability of default. And the third one is expected exposures. And the expected exposure part is the one actually is the main interest of our course, because this one involves simulation of different risk factors, calculations of the expected exposures, expected exposures, and so on. So this is the main part, and also from computational perspective, this is the most expensive one. These two, of course, this is trivial. This is probabilities of default. Those are typically calculated as we could do it for the yield curve, implied from the CDSs, and those are just basically probabilities of default that you can find in any trading system. So this is basically the approximating formula for CVA. Get the expected exposures and multiply with probabilities of default and loss given default, and you are having the adjustment that you have to incorporate in your risk-free pricing such that the value will represent the probability of default of your counterparty. Everything in the derivations for CVA will be perfect, except that there could be some practical issue. Imagine a scenario that you yourself, you have a contract with other counterparty. So then you would like to charge this counterparty additional charge associated that the counterparty may default. However, on the same time, the counterparty may be calculating CVA against you while taking into account probability that you may default. What that would imply is that the derivative price from perspective of two counterparties may differ. Therefore, they will never make an agreement. If you, for example, would like to buy, you think that the value of a swap is 5 because you took into account probability of default of a counterparty. However, your counterparty thinks that the default probability, taking into account default probability of you, value of a swap is 15. Obviously, you will never agree about the price because either of the party would need to neglect the probability of the default of the other side. And that's, of course, problematic. Then, in order to address this issue, the so-called symmetry issue, we have to go into the bilateral credit value adjustment. So BCVA. So this is the topic of this block. So before we were pricing, of course, CVA under the risk-free pricing, and then we were looking into this adjustment for the default probabilities. And of course, the symmetry problem is that if we have an investor, from the investor perspective, the value of derivative will be equal to the risk-free price that we just get from the risk-free measure minus CVA that the counterparty, so the CVA this means from the perspective of I, but this means a counterparty may default. So this is CVA I, the charge computed by assuming that the counterparty defaults. So you see, this is the part from one investor. However, if you have a counterparty will look at the value of derivative equal to the risk-free rate, risk-free price. So this is exactly as here. However, the CVA would be that it's about this counterparty to default. And this counterparty is looking that this one will default. So you see, obviously, of course, everything would be ideal if you have those probabilities of default of two institutions are the same, then indeed those counterparties would agree about the price. However, in general, that's not the case. So if you have two banks, exactly the same risk profiles, then indeed those prices from two perspectives will be the same. However, if the probabilities of default or exposures will be slightly different, then that would not be allowed, because then the prices will be different, there will be no transaction. Okay, so in general, we see that CVA from investor's perspective and also CVA-C, they are not the same, because the two counterparties might be subject to different credit risk value, so that the adjusted value, which is calculated by investor I, is not the opposite of the adjusted value calculated by the counterparty C. In other words, two parties may not agree about the adjusted price. And this is why this bilateral CVA steps in, where we are not only looking from our perspective as the safe investor perspective on the pricing of derivatives, but we also take into account the symmetry that our counterparty will be also looking into the creditworthiness of us. This means that we also have to include the probability of default of us as the party in this contract. And what is also important is that the CVA, so if you have, depending on the perspective, so CVA will be also called DVA from every perspective. So let's take a look here. When deriving the price of risky asset, we do not only include CVA component, but also the component that accounts for the risk associated with our own default. And that is called debt value adjustment, DVA. So if we are looking for the CVA, but for ourselves, that's called DVA. This is basically easy to remember. CVA for counterparty is CVA, CVA for us is DVA, debt value adjustment. Okay, so now let's take a look at the how to create this BCVA fair value price of a derivative, because that's the ultimate goal of this part. So of course we want to impose that, of course, here's the opposite side, and so this is also important, that CVA from counterparty will be equal to DVA from the investor. In opposite, CVA from the investor will look at this like a DVA from the counterparty. So of course this is kind of a little bit of mixed relations, because you always have to look from whose perspective what quantity is CVA and what quantity is considered to be DVA. So everything depends whether you're investor or you're the counterparty, and that could of course vary. So let's take a look here. So for the two counterparties, we would like to have the following pricing equations. So investor's perspective, we have a risk-free price minus CVA of the counterparty, and from the VC we have a risk-free rate minus default probability of CVA that the investor will default. So of course now we would like to impose this condition. So this is not really doesn't really work. We would like to impose the condition that these two prices from investor's perspective and counterparty perspective are the same, and this is what we'll do. We will incorporate, to make this equal, their own probability of default. So we add CVA from C. So in this case, investor's perspective, we subtract, of course, CVA of investor, so counterparty will default, and add the DVA basically, so that our own probability of default and impact on the exposure. So this is the add-in. And the counterparty would do exactly the same. And once we include those probabilities, let's say the CVA from the investors and counterparty perspective, then because it then this will have an opposite impact in the valuation. This means that actually only then the prices from an investor's perspective and also from the counterparty perspective, then the transaction would take place, because both counterparties will consider that the derivative is priced correctly in the sense that they are both taking both counterparties into account when evaluating default probabilities and also the impact of the adjustment that has to be included in the pricing of the risk-free or default-free derivative. So this adjustment that has to be incorporated. Now let's take a look at the formula. Of course, the DVA is the CVA from the counterparty perspective, so it's opposite to CVA, and then the equation looks almost the same, except that we have to look right now at the maximum of, so this is negative exposure, so we are looking at the maximum of minus exposure part. So remember, we were looking before exposure profiles of our swap, right? So this was what we have seen. And for the CVA calculation, we were only looking at the upper side. That was the part we could lose. And from, of course, in a DVA, we also have to incorporate this part that both parties would include that you have to include in the valuation. But of course, the counterparty would do the opposite, and that would nicely match their the expectations regarding the price quoting. And then finally, the BCVA, so this bilateral credit value adjustment, is simply the difference between CVA and DVA. So you see, actually what we have seen is that once you are able to calculate exposures, this is basically unexpected exposures, that's the main part of the xVA. Once you are doing that, actually all those letters that we add in xVA evaluations, they're very much alike. So you add just more elements, however, everything still remains dependent on exposures, and maybe in a different xVAs. It would also depend on some sensitivities, but basically if you have exposure calculations, then at least those simple ones like CVA, BCVA, and also FVA that I will discuss in next block, those are very much straightforward to be calculated using what we have learned in this course. What is interesting also here is maybe another one, this is a little bit of a controversial term, is that if you look at the BCVA adjustment, which is equal to CVA minus DVA, this is also what makes the fair value price between the two counterparties. Then you see that the adjustment will decrease with a depth value adjustment of your own. So this means that we can actually see that that we can see a profit, you can see positive effect of your own default. So once your own default increases, this part will be increasing. This means that the overall BCVA part would be getting smaller, essentially. So this is a little bit of a problematic aspect if we talk about the BCVA evaluations and so on. Here, because we also see this linearity, so essentially BCVA, you can see that also the linear combination of CVAs, essentially, whether it's a positive expected exposures or negative expected exposures, and both they suffer from the same thing that we have also mentioned before about wrong way risk. So in order to evaluate efficiently those terms and assume independence between default probabilities and exposures, then those let's say methodologies for calculating either of them is exactly the same. Computation of exposures and expected exposures, it is really a vital point, vital element of calculations of xVA in general. Of course, there are more complicated value adjustments for which we need much more numerical efficiency and where computations are extremely heavy. However, here we will concentrate on the measures or the adjustments, the value adjustments, for which they rely on the calculations of expected exposures. So far, we have seen that we are able to calculate approximations for CVA, DVA, BCVA, and another measure that we can also incorporate, so another value adjustment that we can compute based only on expected exposures and expected negative exposures is the so-called funding value adjustment. Funding value adjustment, again, as we have seen for the BCVA, would depend on positive exposures, negative exposures. And the formula for this is the formula for the cost, so the funding cost adjustment. We also have an equivalent formula for the benefit adjustment. You can see the formulation. Here, I don't want to go into the details how these derivations can arrive at these derivations, because that would take too much time. I would like to here present the final formula for computation for FVA, which consists of BCA and FCA and FBA. So here you see again integral over time. This is again assuming rate risk, so we're assuming zero correlations between defaults and exposures. We have an equation which corresponds to the expected exposures. Here we have a so-called funding spread. So this typically would be also linked to the cost of our funding for derivatives. So this is called derivative business requires funding. That is expressed by SB. Typically, this funding will be also given in terms of LIBORs. So depending on our financial position and how cheaply we can get funding in the market, typically this will be related to some LIBOR rate available in the market. Of course, you see already at this point, you can see that there is an assumption here that exposure which we have here, the value of our portfolio, does not depend on the funding part. Yeah? You could also argue that this funding, if this depends on the LIBORs or some kind of other interest rate indices, this would also need to be correlated. And of course, in practice, that would be too expensive to compute. It's too difficult also to establish. So this is, you can say, an approximation of that, let's say, the full-blown expectation where all the risk factors are taken into account. Another two parts. Here we have a probability of a default. The default will happen after time t for the institution and also for the counterparty after time t. So this is this probability part that we have also seen in CVA and DVA. So you see all those, there are some assumptions here. So the exposure is independent on a funding spread, also independent of the probabilities of default. You could also try to, or in literature, you can see people attempting to correlate these and also this part correlated with the exposures. That would be the wrong way risk part. And also here, the funding part, you could also link that to the exposure. So depending on what type of, how big is your exposure, you could argue that your funding could be larger or smaller. So if your exposure is extremely high, you could expect that your funding would be more difficult, so your rate should be higher than the one who has a small exposure in the market. So there is a lot of, let's say, economical arguments, what type of effects would be between those. However, again, those are very difficult to measure quantities. So even how to measure the exposure correlation and default probabilities, this is difficult. How to get probabilities of default, this is difficult in the first place. So probability of default, how to get them, this is already rather advanced. And I already mentioned that those probability of defaults are difficult to estimate from the data, especially if we deal with a counterparty which is small. Then those probabilities also will be some kind of coming out of kind of interpolation of CDSs available in the market, and there will be some mapping happening. So there is a lot of heuristics already in this point. So then one can argue what kind of correlation you have between the two. However, from the risk perspective, you would like to have this impact and to see what is your impact on FCA or FVA in general. But here the bottom line is that assuming those independencies, the calculations of FCA, it is purely based on the calculations of the expected exposures. And then we have only one integral in time. Those probabilities of default will be estimated again from the CDSs available in the market. And this is the FBA. So the FVA consists of course, the two elements, FCA and FBA. So the cost and benefits. There are only small differences. The first difference is that we are looking at the negative expected exposures, so discounted negative expected exposures. Then the part for the funding, this is the funding that business generates. So you see that this part we have a negative exposures, and that would allow you to generate some funding. And of course, this funding would be included in the FVA. So FVA includes these two types of funding. the funding that we generate from the business and also the funding that we have to pay to support our existing positions. And those two types of funding would be included in the FVA. Again, here, this quantity here, it will be a spread over, let's say, 6 or 3 or 12 months LIBOR, depending on our business line, on how cheaply or how much we are willing or counterparties willing to fund the positions to keep with us. And this is numerical approximation. Again, this integral, you can see if we simply do time discretizations, so the discretization in time direction, because this part, this quantity, you see we are conditioning on the initial time t0. So this expectation is just time-dependent function. There's no stochasticity, so we can interpolate depending on, even here I made it a little bit more generic, that we have this omega 1, omega 2, that we can play with it according to the weights. Of course, this interpolation here, or this integration here, is very standard, is a trapezoidal, or you can even think of Euler type of integral. And here we have, of course, those SL, which is the funding, which determines the spread of how cheaply, of how, at what rate we can fund our position. From the risk management perspective, it is very important to understand the risk profiles of trades in your net set or in your portfolio. So, for example, if you have a CVA on a portfolio level, it will be excellent to know what are the individual CVAs per individual for all the trades in a portfolio. In that way, you could establish which of the trades play the most role in the contribution in the risk profiles regarding to the value adjustment. That would allow you, for example, from the risk management perspective, to either hedge the associated risks, or, for example, even to sell the position in order to benefit from overall risk reduction that you may expect. So obviously, the benefit, what we would like to have is that if we could have a CVA on for our counterparty I, if we could express it as the summation of all the individuals CVAs for all the trades with that particular net set or counterparty. Of course, this is not equal sign, so the CVA is not additive. So if we have a number of trades in our portfolio, all the individuals CVAs will not equal to the CVA of the whole portfolio. And of course, the reason is that we would see some netting effects also playing a role in the reduction of the risks. So therefore, this equality will never work in that way. However, our objective, of course, is to find a method in which we could express CVA or decompose CVA into individual CVAs. Of course, this is not really a unique way, because you can argue what are the criteria for this assessment. Because, for example, you could say, I have 10,000 trades. I could associate CVAs according to the notional. But of course, that is not really, that's one of the possibilities. But here we would like to decompose CVA for counterparty with respect to the, let's say, their role in the CVA evaluation. So this is the objective of this block. There's another thing that we could think of, is so-called incremental CVA. So if a client would like to get a new contract, what we can do, we can evaluate portfolio with and without CVA. So by having two Monte Carlo runs or two CVA evaluations, we can basically calculate the contribution of a contract, particular contract, to the overall portfolio of the counterparty. So that's, of course, that's called incremental CVA, and that can be performed. However, if we think of this kind of experiment of incremental CVA for the whole portfolio, therefore calculation for those individual CVAs for all the portfolio, for all the trades, that, as you can imagine, it's computationally extremely expensive, because that would require multiple re-evaluations of the xVA engine, and that's typically extremely expensive. So incremental CVA, if you can do it for small scale, that's possible for, let's say, few trades. But if you like to do it in a large scale, the whole book, that rather is impossible. And of course, now the objective here is to find a way how we could decompose CVA or let's say, xVA, because this will also hold for BCVA and FVA, how we can decompose that in a summation of individual CVAs, such that overall they will agree. So the portfolio level and also the sum of individual ones would agree. So the methodology that we are going to apply to achieve that is so-called Euler allocation process, and that relies on a homogeneity function. So there's a function property that's called function's homogeneity. The function f, which is mapping R to n to R, is said to be homogeneous of degree k if the following equality holds. So if we have a function that is a f of a of x, this x is a vector with n entries, and then we have a equal to a to power k f of x, then we say that function f is homogeneous of degree k. And then what holds, what is actually the key element for this decomposition of xVA into individual contributors, such that the sum of all those elements, the total sum is preserved in terms that it's equal to the portfolio exposure. Then we have the following. So we use the following method. Suppose function f is continuously differentiable in Rn, then f is homogeneous of degree k if and only if the following holds. So here we have k times f of x is equal to summation, and then we sum of all the elements of over this is size of vector x, and then we have a derivative of this function to each individual element of this vector times xi. So if we have a homogeneous function of degree 1, this is very nice, a very attractive formulation, that function x can be represented as a sum of all the partial derivatives multiplied by individual entries of that vector. So this is nice quality. And this is the quality we are going to use in the decomposition of the CVA, or let's say in general, expected exposures. So this is the relation. So if we have sensitivities, if you can also think of yield curves. If you have sensitivity of yield curve to say of your payoff to individual discount factors that your function your payoff depends on, you can also represent PV, present value of that trade. Of course, this would only hold for linear products. So this homogeneity would only hold if the function f is linear. There are also other constraints here, so you cannot expect that this would work also for nonlinear functions. So our objective is to find this decomposition of CVA into sum of, here we have n trades in a portfolio. We would like to sum of all of those i's, so CVA first one, second, and so on, depending on number of trades. Of course, CVA we already have seen in this lecture that is essentially expected exposure multiplied with probabilities of default, and that's basically integrated. So essentially, if we just start with the expected exposures, then we have that we basically equivalent. Yeah? So this is basically a small adjustment or transition between CVA and expected exposure is basically trivial. So if we start with expected exposures, this is what we have. So we have n trades. We sum portfolio or the net set for all the trades, and we have also discounting part to today. So what we can do, we can reformulate each of individual trades in the following way. So each xi, so introduce new variable xi, which is equal to VIT divided by alpha I. So this is, you see, if you substitute xi here, everything will nicely cancel out. So then we end up with here. And of course, now we see those xi's. Here we have, this will be equivalent with our function f alpha. So you see that now we have evaluated, we computed those exposures, the value of our each individual trade at each individual time, and we weighted with some alpha coefficients. So now this function f, of course, it's a function. This is smooth function. Also, those terms in alphas, everything is smooth. Those are just, we assume here also linear products, so there is no problems there. And now the next step would be to derive, of course, express this expected exposures as f from alpha, because this is what we said here. So this is equal sign. This will be a summation of all the alpha i's, and then we have this derivative of each individual exposure, discounted exposure with respect to alpha. One can wonder what is the benefit of this representation. And actually, if you look at this expectation here, and what happens here is that if we calculate this exposures VIs, we are essentially looking into derivative with respect to alpha I. This means that if we have those exposures, we don't need to recalculate those exposures. We need to only calculate sensitivity with respect to alpha I. This means that from the computational perspective, if we have exposures, if we have computed the exposures for all the trades in the portfolio, that's very cheap because we just basically have to evaluate some vector with samples, portfolio values for all the risk factors, but we don't need to recalculate the portfolio values for all the risk factors. So you see that basically our VI stays intact. We only need to calculate derivative with respect to all this expectation with respect to alpha I. And of course, an xi or VI stays the same. So that's basically from numerical perspective, that's very beneficial. So in this way, actually, we are able to arrive at this nice representation. So you see that each of those, if you reformulate, if you go back to the CVA, that each individual CVA for each trade, because this is number of trades here, can be expressed in some way in as this kind of ratio. And this derivative is essentially calculated from this expected exposure, but for that derivative, we don't need to redo the Monte Carlo simulation. We only need to store the results, the exposures of the portfolio for a given time. So this is basically the whole idea here, and that basically allows you to reduce significantly number of computations. You don't need to redo your CVA. On the other side, it is still relying on this homogeneity assumption. So of course, everything depends on your portfolio combination, what are whether the condition is satisfied or it's not. But at least in this way, we are able to express the CVA as the sum of all the individual CVAs, of course, using this property. Of course, this is not necessarily unique. You can think other weights, for example, that you can find the contributions of each individual trades in the overall CVA. In today's lecture, we concentrated on xVA. In particular, we have discussed the simulation of the expected exposures, potential future exposures, and then we applied those in order to evaluate CVA, DVA, BCVA, and also I showed you how to do it for FVA. So let's wrap up what we have learned today. We start with introduction to the basics of credit value adjustments, and also we discussed the exposures and potential future exposures. So those two were elements. The first one we discussed why the need for CVA actually appeared. What were the motivation from the regulator to introduce this kind of measure and also adjustment of derivatives, why to look at the default probabilities of a counterparty, and later how this is related to calculation of exposures. Once we have exposures, of course, the next point is to calculate expected exposures. So there we have used the Monte Carlo simulated values of a portfolio, and we evaluated discounted expected exposures. And also we have this discounted negative expected exposures that can be used in a DVA calculations. I have also presented, before we went to this, let's say CVA, I also have shown you some of the nice sanity checks for your simulation, where you can basically, from a theoretical perspective, you know exactly what the expected exposure would be. And that was especially in the context of an interest rate swap, which was related to swaption. We also had a stock that was related to call option. And also we had foreign FX swap that become also an option on the underlying FX rate. So those were nice sanity checks that if you have implemented in Monte Carlo and xVA evaluation, you can always check whether the contribution or whether your implementation for expected exposures, whether it is equivalent with analytical representation. It's always good to have. Then we went to a Python simulation where we discussed the 1D case where we simulated whole white model. And based on the whole white model, we analyzed the impact of netting on a portfolio on two swaps. So first we had simulation with a single swap. Also we had simulation with a multiple, with two swaps. And we are observing what is the impact of those two swaps, how we can observe the netting effects if we have a portfolio of these two derivatives. Of course, in the code, you can also extend with multiple dimensions and also multiple swaps. That's very trivial to extend that code. Next point was the explain you how to extend the code and also the calculation of expected exposures if you have multiple risk factors. We discussed here in particular possibility of inclusion of effects, but this would also be equivalent if you do it using inflation that we have discussed previously in this course, and even other risk factors like, for example, stocks that they were covered in a course of computational finance. Then we went, so the core point was, of course, the expected exposures. Then the next step is the calculation of CVA. So I have shown you what the motivation, step by step, we went through the derivations of CVA, how take into account default probabilities of a counterparty, and how to arrive essentially at the approximation that is accepted in the financial industry. As a natural extension of CVA, we went to BCVA. In this case, we included not only of a risk probability of default of a counterparty, but also probability of default of our own. In that way, we were able to find, let's say, symmetry in prices from our perspective and also the counterparty perspective. And then the further application was the funding value adjustment. So I showed you that once you have expected exposures, once you have performed the full simulation of your portfolio, you can simply apply that to evaluate FVA. So there's many letters from the xVA you can use, and many adjustments you can evaluate once you have computed expected exposures. So again, the most expensive part from the whole xVA business is how to compute exposures for a given portfolio. That's typically the most expensive part, and a lot of attention from the industry is concentrated on how to facilitate faster evaluation. For example, not only by the end of day when a bank is revaluing all the positions and books, but for example, also intraday. If you can do it very fast using GPUs or CPUs or some smart modeling choices, that will be always beneficial for the industry. And then we talked also about the attributions. So how to decompose xVA into sum of individual elements, the risk contributors. So here in particular, I was looking at the CVA, that we could express CVA in sum of, let's say, CVAs, that in reality, CVA is not really additive, so we cannot decompose trades in individual CVAs, and then you can sum them up. That will equal to the CVA of a portfolio. And however, I show you a methodology that would allow you for this kind of relation. Of course, that relation is not unique in the sense that you can find multiple or infinitely many combinations of this approach, but this is a really nice, elegant methodology how to achieve that. And now is the time to summarize the lecture and also the homework. I would like to give you the homework. I have prepared 3 exercises for today. The first exercise involves Maxwell School-wide, and here we will be simulating stocks. So I have defined, model with 4 dimensions. So we have 4 stocks with different volatility parameters. All of them, they depend on the same interest rate process, RT. This will be full white model. And we have some, those parameters you can choose yourself. We have also the correlations between Brownian emotions. So this is also what you have to specify. The next step is to define a portfolio with 10 stocks of stocks 1, 20 stocks 2, 5 stocks 3, 10 interest rate swaps. So we have to choose different interest rate swaps that will be defined in terms of interest rate, short rate here. So you have to choose different configurations. And also you have to add 5 call options into your portfolio. So with different strikes and different maturities. So this is first, we build up a portfolio, and then you have to perform some measures. The first one is to calculate expected exposures, potential future exposures, and then given some probability of default. So we have 5%. So this is just, you can choose 5% and a recovery rate of 25. Then you have to perform the CVA evaluation, and we have to discuss the results. And Then the alternative and also the additional part is to discuss the netting effect and how would you, what kind of derivative you think would fit to the model, to the configuration you have just seen, such that you can reduce the exposure in terms of expected exposures and also potential future exposures. So we have to look from the as a risk manager, looking what are the risk profiles of our portfolio and how to reduce them, what kind of derivative to add, such that this reduction will be the most efficient. And also don't try just to do the opposite. So minus 10 stocks, minus 20 stocks, and minus 5 stocks. That is not the idea here. You would like to hedge your position using as few additional positions as it is possible. And then another part. So we have a first exercise. First exercise is here, and then we have I have only 2 exercises. The second exercise is to confirm numerically that expected exposures of a swap, so we have an interest rate swap, it is equivalent with pricing of swaption. So essentially what you have to do is to simulate expected exposures from the code we have seen in the lecture, and then you also have to implement a swaption pricing based on a full white model. This is also covered, I think, lecture number 7 and 8. And then you have to compare, using, of course, Jamshidian trick, you have to compare the two. So we have 2 exercises for today. The one is more, this is a bigger exercise where you have to simulate processes, build up portfolio, and become a risk manager and evaluate CVA, and then look also from the netting perspective on how to reduce the risks. The second part is more like a sanity check whether the implementation is correct. So you have to implement the expected exposures for interest rate swap and compare the values with the evaluation obtained from swaption based on a full white model. So this was it. So I hope you enjoyed this course, this lecture. We still have 2 lectures to go. So next time we talk about value at risk, and also we will reuse a lot of knowledge we have learned today. So see you next time. Bye.